In this video, we are going to learn about limits at infinity and horizontal asymptote. So there are two different concepts. One is called the infinite limits. The other one is called the limits at infinity. So what are the infinite limits? Let's look at this graph. And if you look at this graph, and you can see that when the x value reaches 3 from both sides, when x reaches from both sides, from right, and you can see the function goes to negative infinity, and then if x reaches 3 from the left side, and you can see function goes to positive infinity. So those are what we call infinite limits. So you can see in this case the changes are vertical. So vertical changes, you talk about vertical changes, so go vertically. So when you go vertically, you talk about infinite limits, and then it's also produce what they call the vertical asymptotes. So we learned about this one earlier. So if you did not learn this topic, you can see there's a link in the description, and then you can learn about infinite limits. So goal of this video is to learn about the other one. So what's the other one? What we call limits at infinity. So in this case, what happened is the changes are horizontal. So last time you happened like say we talk about vertical. So vertical asymptote. Now we talk about changes are horizontal. So what we mean by that? For example, let's look at this graph, and then let's look at the situations, and you can see what we're trying to do right now is we're gonna see what happened when x become extremely large, or what happened when x become extremely small. So that's the situation we try to understand right now. So what happened when x goes to infinity or really large, or what happened when x goes to negative infinity, and then we can see what is the behavior of the function in this situation. So let's look at an example. So let's consider this function fx equal x squared minus 1 over x squared plus 1. So we know that this is a rational function, and degree of the numerator and denominator are 2, so same degree. So you can see there's something interesting going on here. So you can see when when x goes to infinity, that means when x getting larger and larger in both sides, so we can say plus or minus infinity, so it doesn't really matter, so both infinities. So when x become really large, extremely large, and you can see that x squared is what we normally call x squared, I think it should be better to say x squared will dominate. X squared will dominate. X squared will dominate the term. So what does that mean is when x become extremely large. So this is the very interesting situation. X is extremely large. When x is extremely large, and you can see if you look at the numerator, it is x squared minus 1. So when x is large, x squared is really large. So then subtracting 1 doesn't do much difference. And the same thing will happen at the bottom also. When you have x squared plus 1, you can see x squared is really large. Then you can see plus 1, you can, what we normally call, you can neglect it. So you can see, so dominate the term. So dominate the term, and you can see, the effect from minus 1 and plus 1 are the effects. So you can see effect from minus 1 and plus 1 can be neglected. So it's a like really interesting argument, can be neglected. You can see can be negligible. Can be negligible. So you can remove, we can ignore the effect from negative 1 and plus 1. But remember, we cannot do that in other situations. We can only do this when x goes to infinity, either both infinities, plus or minus infinity. Then you can do that. You can ignore the smaller terms. You can ignore the smaller terms. So what happened in this case? So you can say thus. So what happened here is you can see fx looks like it getting closer to, from the numerator it looks like x squared. And from the bottom, it looks again like x squared, because those are the two terms that you can find here. Those are only the largest term, or what we call the dominating term. So when x goes to infinity, what matters is the dominating term. We don't need anything else. So that means, but what happened now, they get simplified and you end up getting, in this case, 1. So this is the interesting thing. So what does it mean when x getting large and large? You can see the fx function getting closer to what value? To 1. When x goes to infinity, is the function getting closer and closer to 1. And similarly, and you can, and in this case you can say as x goes to infinity. So in this case, both plus and minus infinity, both infinity. Because you can see when x goes to negative infinity, the same thing will happen when it's square. And you can see, you can ignore negative one and positive one. Okay, so now what does that mean? In other words, if you use the notation, so you can see, we can say this one, then we can write this one as limit when x goes to infinity. That means when x is really big, getting larger and larger indefinitely. There's no limit there, indefinitely. X squared minus 1 over x squared plus 1. We can say this one actually approaching the value 1. Since we took a limit, we say equal 1. And similarly, on the other side, you can write the same thing. You can say when x become extremely small, that means not in size. So actually what we talk about extremely small means like you can it's not like small in size. So it's like with the sign. So like negative 1,000, negative million, those are the kind of things we are talking about here. And the same thing, you have x squared minus 1 over x squared plus 1. Again, you can see in this case you get 1 again. So that is the situation, what we normally call the limit at infinity. And you can see that we are talking about two infinities here, positive infinity and negative infinity. So what happened in this case? So that is what we call the limit at infinity. So in this case we can see the limit at infinity is simply 1 in both cases, but it's not always the case, and you might get two different values in certain situations. Okay, so so let's look at some graphs now. Let's look at 3 graphs. In the first one, you can see that it starts with some y value which is bigger than L, and then cross the dotted line, and then we can see that when x increases to infinity, and you can see that the curve getting closer and closer to the line L. So that's what happened in the first one. So let's look at the second one. In the next one, you can see that it starts with a larger value, and then it continue to decrease and reach the line L when x increase, when x getting larger and larger. So this is the second situation. Let's look at the third one. The third one is really interesting, and you can see that it fluctuates, it oscillates, and around the line L, around the value L, and then you can see when x increases indefinitely, and you can see that this line, the curve, are getting closer and closer to the line L. So this is very common situation. Like this can happen in most of the vibrations that happen in nature. Like for example, if you have a pendulum, and if you swing it and release it, and this is the kind of situation it's going to happen. It's going to go it's gonna vibrate, it's gonna oscillate, and then you can see it's gonna reach a value. So this is the kind of situation. So those are all nice examples of what happened at limit at infinity. So let's look at a definition now. So what the definition says that, so let's say you have a function, let f be a function defined on a open interval. So you can see this is an open interval. Then we say the limit x goes to infinity fx equal L. So we say when x goes to infinity fx equal L, that means that fx can be made arbitrarily large. So you can make fx can be made arbitrarily close to L, arbitrarily close to L, arbitrarily close to L by making x sufficiently large. So what it says that you can make the function value close to L, as close as you want, by picking a value which is very large. So you can make the large sufficiently large. So depending on how close you want to go. So if you don't want to go that close, you don't need such a big value. But if you want to go really, really close, then that means that that's why it's sufficiently large. So depending on how close you want, you pick a larger value. So we write it like that. So that's the idea. So that means by picking a larger and larger values, and you can see that you can make fx close to it, as close as you want. Okay, so that's the idea. And similarly, we can also write this one. So in a similar idea, so that means if x goes to negative infinity, if x goes to negative infinity, that means get sufficiently small. That's how we call it, sufficiently small. Then you can make the function close to another value, let's say L. So then it's a similar idea. Okay. Now let's see how we can use this idea in an application. For example, you know like how to find the horizontal asymptote. In pre-calculus, we find it in a different way, like for special situations. Now we simply use this limit at infinity to find all those horizontal asymptotes. So let's look at the definition first. So what it says that the horizontal asymptotes. So it says that the line y equal L. You can see this is a horizontal line. So here's a y equal, you can just say L. So y equal L is called a horizontal asymptote of the curve y equal fx if one of them is either the first one, a limit when x goes to positive infinity equal L, or when x goes to negative infinity of fx equal L. So only one is enough. So you can see in a graph, this is the situation we are talking about. So you can say so we have this line. So what should happen is the graph in one way, at least one way, is to reach the function the value L as x goes to positive infinity, or when x goes to negative infinity. So if one of them is true, then we call this value L. So we can say this line, you can see it's a horizontal line, it's y equal L line is a horizontal asymptote. Only one is enough because there are certain situations you're going to get more than one horizontal asymptote. So there can be either two, one, or no. So only those three situations. So let's look at some special cases now. So the first one is one condition is enough. That means if either x goes to infinity equal L, or either when x goes to negative infinity fx equal L. So only one is enough. We don't need both of them. Only one is enough. Okay, so the second one. So the second one says the polynomials do not have linear asymptotes, either horizontal or vertical. So the polynomial do not have any linear asymptotes, but it can have nonlinear asymptotes. So that's like an advanced topic that we learn in some advanced courses. For example, if you look at y equal, let's say 3x cubed plus x minus 3, something like that, and you can see that when x getting larger and larger, you can see we have cube terms here, and then these you can neglect because you can see when compared to x cube, when x is really large, this doesn't happen when x is small. So if x is really large, and you can see that this is like almost like 2x cube if x is large. And then what happen is this is going to produce an asymptote, but this is not linear, it's non-linear asymptote. So you can see this happen as x goes to infinity. This is like special case. You have to say it as x goes to infinity or negative infinity. So that's what happens. You can ignore the small terms. So so we have like what they call non-linear asymptote. These are non-linear. So yeah, this is not a topic for this course. These are non-linear. It's asymptote, but it's non-linear. So these are a little advanced topic. Okay. So you can learn this in a different course. So let's look at the next one. Number 3. So this is about rational functions. So this is an important fact about rational functions. So what it says that the rational functions may have at most one horizontal asymptote, and there may be multiple vertical asymptote. But the important part is there can be only one horizontal asymptote. And you know how to write a rational function. Rational function means any function that you can write as a ratio of two polynomials. These are polynomials. So if you write two polynomials, if you divide two polynomials, you get what they call a rational function. And what it says that the rational function can have at most one horizontal asymptote. There can be more than one horizontal asymptote, but and then there can be several vertical asymptotes. So, but there may be situations the rational function do not have any horizontal asymptote. So that we can talk about later. Okay, so this is important fact about rational functions. At most one horizontal asymptote, maybe more than one vertical asymptote. But there are situations there are no vertical asymptote also, but say may have several. Okay, may have several vertical asymptotes. So you can think of a function which because you can see that the vertical asymptote, we talked about those vertical asymptotes earlier. So you can see where this is coming from when this denominator function are getting closer to 0, right? When the denominator getting closer to 0, you get those vertical asymptote. But the thing is that there may be a function where denominator cannot be 0. For example, if the denominator equals to, for example, let's say x squared plus 1, and you can see this never gets 0. So that means there are no vertical asymptote for this case, for a rational function like that. If the denominator is not equal to 0, cannot be 0, then there are no vertical asymptote. But there may be a situation where, for example, if you look at the denominator that is equal to x squared minus 1. So if the x squared minus 1, you can see then there are two cases where the denominator can be 0. So that means you can get two vertical asymptote depending on what is in the numerator, because there are sometimes those factors get cancelled. So if you are not familiar with how to find the vertical asymptote, and there's a link in the description, you can watch the video about how to find the limit at infinite limits and the vertical asymptotes. Okay, so let's look at the next one. Next one is the algebraic functions. If you look at certain algebraic expressions, so you can see those algebraic expressions or inverse trigonometric functions, not all of them. Some inverse trigonometric functions can have more than one horizontal asymptote. Let's look at this one. So you already know one function, one inverse trigonometric function, which has two horizontal asymptote. For example, y equal arctan or tan inverse x. So if you look at the graph of tan inverse x, you already know this graph. So it looks like this one, and then you can see there are two horizontal asymptote for this one. So there are two horizontal asymptote. One is negative pi over 2, and the other one is positive pi over 2. Yeah. So this is the graph of tan inverse. This is something you have to remember because this is very useful if you are in engineering, physics, of course, mathematics. So we use this graph a lot, and you can see there are two horizontal asymptote, one at positive infinity and one at negative infinity. Good. So this line is, you can see y equal pi over 2. This one is y equal negative pi over 2. So those are the two horizontal asymptotes for this one. Okay, so let's look at a exponential function. For example, if you look at y equal ex minus e minus x divided by ex plus e minus x. So one is a minus, one is a plus. And if you look at these two, how many asymptotes you're going to see that? So we talk about, you can see the denominator can never be 0 because these both are positive terms, so this is always positive. So that means there are no vertical asymptote. So there are no vertical asymptote for this one, but there are two horizontal asymptote. There are two horizontal asymptote, and so that's interesting. So there are two horizontal asymptotes. Why there are two? And you can see if you look at the limits, if you look at the two limits, and you can see those limits are different. Look at remember the argument that we talk about, the dominating term argument? We can just use the same argument here. So you can see when when limit x goes to positive infinity, y. So what happened when x goes to positive infinity? You can see these two terms are small, very small. This one is very small, this one is very small. So remember the graph of e to the negative x? Graph of e to the negative x is like this. So what happened when x goes to infinity? It's passed through 1 and becomes 0. So getting closer and closer to 0. So that's a graph of e to the negative x. So because of that, what happened? Those e to the negative x terms get cancelled out. So you only, those are neglect. So you only get ex by ex. Ex by ex means the limit is simply 1. And the interesting part is if you look at the limit from the other side when x goes to negative infinity, y. See what happened now? Now what happened if you look at the other graph? What's the graph of e to the x? Graph of e to the x is this, right? Pass through 1. That's the graph of ex. So what happened when x goes to negative infinity? When x goes to negative infinity, this goes to 0. It goes 0. So what happened now? You neglect the other term. You can see you're going to neglect these two terms. Because those are small now. So once you neglect those two, because those are small, you get the other two terms. So when you get the other one, you can see it is negative ex, negative e to the negative x divided by positive e to the negative x. So e to the negative x get cancelled out. So these two get cancelled out. And then you're going to get negative 1 over 1, which is negative 1. So you get negative 1. So that means there are two different values for two different infinities. So you get two horizontal asymptotes for this one. So it's special situation. So it's a good idea to remember special case like. But we can do one more later. That's like a little complicated. You need a little bit more algebra for that one. Okay. So let's look at this graph and see how you can find all those two type of infinities. So let's look at this problem now. Let's look at this graph, and this have multiple asymptotes here. So let's try to find these for this graph. So find the infinite limits, those are the vertical ones, and the limits at infinity, those are the horizontal ones, the vertical ones, the horizontal ones, and then all the asymptotes. Let's go one by one, and then you can see at negative 2, you can see the function goes to infinities. So that means those are the limit, infinite limits. And also at 3, you can see on one side goes to negative infinity, one side goes to positive infinity. So let's write them. So we have infinite limits. So we have limit x goes to negative 2 from the negative side. You can see the y or the function is positive infinity. And also we have limit x goes to negative 2 from the positive side, the larger side, and you can see it also goes to infinity. So this says that y, not y in this case, because it's like a vertical line. You can see x equal negative 2 is a vertical asymptote. Only one is enough, but we have two now. And then also you can see limit x goes to 3 from left side, y, the function y goes to negative infinity, and the limit, and you can see x goes to 3 from the positive side, y goes to positive infinity. When you go from the positive side, it goes to positive infinity. When you go from the negative side, it goes to negative infinity. So that means again goes to infinities. So that means this says that again you don't need both. You only need one is enough. But we have both. We have two here. So you can see again x equal 3 is a vertical asymptote. And also you can see that part B. So we are also answering part C at the same time. Part B says that limit, if x goes to negative infinity, y, And you can see if x goes to negative infinity, if x goes to negative infinity like this way, you can see function reach the value 0. So reach the value 0. So that implies that y equals 0. That's the value. Y equals 0, right? Is a horizontal asymptote. And also, you can see in this one you have two different values. So the limit when x goes to positive infinity, when x goes to positive infinity, and you can see the function reach the value value 2, right? Value 2. So it is 2. So that means you can see y equal 2 is a horizontal asymptote. So there are two vertical asymptotes and two horizontal asymptotes for this graph. Okay, so let's look at a nice theorem, and then we do multiple examples also. So let's look at the next one. Nice theorem that's very useful. So what this theorem says that if you have any positive number, so you just pick a positive number, and then what it says that the limit when x goes to negative infinity, the limit of 1 over x to the r is 0. And this is clear. The reason is, and you can see x is in the denominator. So that means when you make x large and large, since x is in the denominator, the fraction goes to 0. So this is a simple idea because you are making the denominator large. Same thing when x goes to negative infinity, you can see you are making this fraction smaller and smaller and smaller, so it goes to 0. But in this case you have to be very careful because when x goes to negative infinity, if r is like, for example, let's say 1/2, then you try to find the square root of negative numbers. So that's why I say if it exists, because you have to be careful what kind of r we use when x goes to negative infinity, because sometimes this quantity might not be exist. Okay, so be careful with that. So it's only when this quantity exists. So for example, r equal 1/3 doesn't have any problem with this one, but square root, like for example r equal 1/2 has a problem. Okay, so so this is like a very clear situation, because what happened in both cases, and you can see this fraction, so it's getting smaller and smaller and smaller. That's what happens. It's getting smaller and smaller, so it goes to 0. So same thing. So even on the other side, and you can see what happened is it's getting smaller and smaller. So for the negative side, again when it exists. Okay, so let's try to look at a interesting example now. So evaluate the limit when x goes to infinity, 3x squared minus x minus 2 divided by 6x squared plus 4x plus 10. So you can see this is a rational function. So when you have a rational function, there's a special strategy. What we're trying to do is we're going to divide the top and bottom by the largest x power in the denominator. So we divide the top and bottom by the largest x power in the denominator. So let's do that now. So we're going to get this. So what we do, we can divide the top and bottom by the largest power in the denominator, so it's x squared. So we divide the top and bottom by x squared. So if you split, what you're going to get is you're going to get this. So you're going to get, so divide each term by x squared. So we get 3 minus 1 over x minus 2x squared divided by 6 plus 4 over x plus 100 over x squared. So what you did, you divide each term by x squared. Okay, so now what happened, using the previous theorem, you can see from the previous theorem, you can see that when x gets large, you can see all those terms goes to 0, because you can see that there's x term in the denominator, so all of them are 0. So once all of them are 0, all those terms goes away. So that means your answer is going to be 3 over 6. In other words, 1/2. So that means you can see the limit is 1/2. So in other words, 1/2 is a horizontal asymptote in this case. So you have a horizontal asymptote, y equal 1/2, and then you can see there are no other asymptotes because you only get one value. You only get 1/2 because we have the same result. We all those terms go to 0 even when x goes to negative infinity, because we know that this extra information. You can see limit when x goes to negative infinity, you also get the same answer. So that is the reason why polynomials do not have more than one horizontal asymptote. So you can see even when x goes to negative infinity, there's still 1/2. So there are no two values, the same value. You get the same value. Okay, so these are the limits at infinity. So in a separate video, we do have multiple like a problem solving video, so you can see more examples in that. So this is the basic theory about how to find the limits at infinity, both positive and negative infinity. Now try to do these problems as practice problems. Now try to do the following as practice problems, and you can find the answers in the description. And after this video, we're gonna go to some special limits, also some difficult problems. So you can look at that as extra problems video.